welcome to our last session of the conference. It's my pleasure to introduce Shabbir Ahmed. So Shabbir got his PhD back in 2000 from University of Illinois, Urbana-Champaign. And he has since then become a renowned researcher in stochastic optimization. He has made some very important contributions to many areas within stochastic programming. For example, the chance constraints, risk measures, sample average approximation, applications to production planning, and his name has become very much associated with those areas. But he has particularly taken a leadership in the sub-area of stochastic integer programming, where he has been applying some nice techniques from integer programming to the stochastic context, and being able to solve these very challenging problems, even in the multi-stage case, more recent paper by him. Shabbir has also done quite a bit of service to our community. He was chair of Stochastic Programming Society between 2007 and 2010. He was also vice chair of Inform's Stochastic Programming section on optimization, which means that for 2 years he was unifying the belts, right, as they say in boxing. And he's also his editorial work. He's also associate editor of a few journals, such as Mathematical Programming Computation, Operations Research Letters, Optimization Methods Software. Quite a list is quite long. He has also, and because of that, all the service and research, he has been recognized. His work has been recognized with several awards and honors, of which, again, I won't go through the long list, but mention, for example, the NSF Career Award, and more recently, the Dean's Professorship and Stewardship Fellowship from Georgia Tech, where he's a full professor now. So it's an honor for us to have him close the conference with some stimulating talk on the blessings of binary in stochastic integer programming. So please welcome Shabbir.
All right. Well, thank you for that long introduction, and thank you all for staying. I have been repeatedly told that I'm kind of holding everyone back from enjoying the day outside and kind of be on your way. So I'll try to kind of wrap things up in time. So the title of the talk is Blessings of Binary, and so my goal is to kind of tell you how binary variables in stochastic integer programs can be exploited to develop very effective algorithms. So the main message that I would like you to take away from this message is how these binary variables kind of allow us to do things which may not necessarily be possible if the variables were not binary. So let's jump right in. So let's start with a kind of canonical deterministic formulation of a problem. So we have a finite number of periods, time period t. We have, for every period, we have some decision variables, xt and yt. So here I am explicitly distinguishing between two sets of variables. So there are what I call state variables, and then there are local variables or stage variables. So state variables are the ones which basically link successive decision stages together. So here, for example, is the constraints associated with the time period t, and we have the decision variables of time period t, but they depend on the decision that was taken in the previous period. Now, I'm only talking about successive stages, but obviously you know that with modeling, you can have other types of dynamics that can be modeled. So this is without loss of generality. I'm going to stay in the space of linear objectives and constraints, so constraint systems that look like that, and my variables are going to be in generally mixed integer, but they're going to be bounded. All right, so this is kind of the deterministic formulation. So if you want to do stochastic programming, so there is an underlying process where the data for the problem is being generated, and the decision dynamics are, we observe the information, and then based upon the previous stage's action, we take the current action. So this is the specific decision dynamics, and this is a formulation that you all know. We are interested in the expected value problem, so we are trying to minimize the expected total cost in a nested setting. Okay, so there are plenty of applications for stochastic integer programming. I don't have to convince this audience, but I just want to kind of, energy obviously is huge in this meeting and in this country. There's an interesting book edited by Stein Wallace and Zimba on kind of applications of stochastic programming, and a third of those applications are actually on stochastic integer programming problems. So in some sense, so there is, this is indeed very relevant kind of a topic. Of course, this is a very difficult class of problems. So, it combines these difficulties that comes from not just the uncertainty, not just the dynamics of the problem, but also the non-convexity, the integrality. So it sits kind of at the interface of all of these different complexities. So therefore, it is a very difficult class of problems. But, there has been very, very nice progress, interesting progress. So, and, some of the drivers are, there's been great strides made in integer programming, deterministic integer programming. And, here's a book by one of my colleagues at Georgia Tech, where, there's been very, very substantial improvements. There have obviously been, which as you all know, very, very substantial developments in stochastic programming by another of my colleagues at Georgia Tech. So I get to learn from kind of the experts in both of these areas to kind of put things together. And of course, we have computational power now to actually process problems, and the data actually motivates models that actually have stochasticity in them. So I kind of looked up on Google Scholar, I tried to look up the total number of papers that use the keyword stochastic integer programming or stochastic discrete optimization and all kinds of variations. So I kind of collected this information, and so here's what I'm plotting on kind of 5 yearly intervals. Since 1966, the number of papers with those keywords, just from Google Scholar. And so just as a historical note, an interesting article that I found was from 1967. So this is actually a technical report from the Army, where they use the words stochastic integer programming for diet planning. So I didn't find a model, I didn't find a solution approach, but this is something that is mentioned there in this report. So I thought that was very interesting because 1967. I mean, the birth of integer programming is like 65, and from then on. So this is a very, very interesting kind of article that I found. Now, as you can see, there's of course a sprinkling of papers since then, but something happened in the late 90s, right? So and then when things kind of spiked up, and so kind of here are some of the pioneers. We're fortunate to have many of them here, where basically that laid the foundations of the mathematical foundation of stochastic integer programming. And so that was a fantastic time. There's a lot of activity, and we have been building on top of this. And there's another thing that happened during that time as well. This was the release of Simplex 6.5. So this is a fundamental development in the world of computational integer programming. And I'll show you a plot in a while. So this was released in 1999, where that gave remarkable advantages for being able to solve integer programming problems truly for the first time, realistic scale. So here is a chart. Many of you have seen this probably. This is from Bob Bixby, who was the author of Simplex, where basically this is showing the version-to-version speedups of Simplex, from going from 1.2 to 2.1, and here is the one that goes from 6 to 6.5. So these are kind of the individual version-to-version speedups. So, going from 6 to 6.5, this was a factor of 10x speedup. And, up until Simplex 11. So right now we have what, 12.6? Yeah, so there are more versions afterwards. But this is a cumulative factor of about 30,000. So 30,000 times speedup. Of course, this is on a benchmark problems. This is machine independent, by the way. This is not due to computational power. It is on a set of benchmark problems, but it is indicative of the improvements that we have in solving integer programming problems, deterministic integer programming problems. So in that sense, I think we are in a good situation to be able to exploit these immense algorithmic power that is in this software to go towards trying to solve stochastic integer programming problems. Okay, so another thing that I wanted to point out, the 10x speed up here was primarily due to the implementations of very strong theory that was developed in the integer programming world. And so, somebody sat down, and kind of looked at all the papers that implemented different types of cutting planes and basically implemented everything. And this is where a lot of the speed up comes from. Okay. So I'm going to talk about a specific class of problems. So I'll give you the problem setup. Then I'll talk about this multi-stage, this stage-wise decomposition of the problem. If you read the abstract, there's a plan for talking about a scenario decomposition approach also. But I know it's late, it's after lunch. This is Brazil. We're going to go home in a while. So I'll take a two-stage approach. If we have time, I'll mention a little bit about it. Otherwise, I think talking about the stage-wise decomposition will be good enough. All right? All right, so let's jump in. All right, since I'm interested in solving these stochastic integer programming problems, I'm going to assume that we have a finite tree in the back of the model. So it is a scenario tree. It may be explicitly constructed from data, have sample discretization. It doesn't matter. I'm not an expert in this. I don't know how the scenario tree came. Some of you are. You've given the tree to me. One thing that this may not be an explicit tree. It might be defined by some Markov chain. So in particular, it could be just independent realization, as is in the SDDP method. We have independent realizations in every time, and that kind of encodes a tree. All right? So just some notation a bit. So a node of the tree is node n, and its parent is a of n. Okay, so now once there is a tree, it is in my comfort zone. It is a large-scale deterministic integer program. So here, xn, yn is the decisions associated with node n of the tree. This is the cost objective function. These are the constraints associated with node n. And as you can see, these are the linking kind of variables, the parent node affecting the decisions in node n. And so these are the probabilities associated with, the exact probabilities associated with node n. So this is a large-scale optimization problem. But it has very special structure. So obviously that has been exploited in the linear programming setting by using, for example, in nested Bender's decomposition and in the scenario decomposition way, like in progressive hedging and other types of dual decomposition. What I am interested in, and my problem setup, is when we have these state variables. Remember, I explicitly distinguish between state variables and stage variables or local variables. The state variables of my problem are pure binary. Okay, so now this is, of course, a restricted set of problems, and this is not without loss of generality by any means. But it is possible that we can approximate any general state variable under some assumptions fairly compactly with binary variables. So what this result says is the following. So if we have complete continuous recourse, what this means is that if in every node the problems are feasible, but you have continuous variables that are continuous recourse variables, so that allow you to take care of the infeasibilities, then any multi-stage stochastic integer program with D general state variables can be approximated to epsilon accuracy in the sense of the objective function by another problem with k binary state variables, where k, the number of binary variables that you introduce, depend only linearly in the original dimension and polynomially in the accuracy, right? So log of 1 over epsilon. So of course, this complete continuous recourse allows us to kind of have some kind of measure, have the value functions to be continuous, which is not true in general, and that allows to get Lipschitz estimates to get these error bounds. And so this kind of just follows from fairly well-known sensitivity theorems in mixed integer linear programming. So, but what does this really mean? So, for example, if you have, you're measuring the water level in a reservoir, which is, in general a continuous variable. So one way to deal with it would be to discretize it. So let's say in meters or half a meter, and that gives you an integer variable. But then you can take a binary approximation of this integer variable. So if you have 100 levels, you introduce log of 100 binary variables. And that allows you to get a small number of binary variables to represent this integer with 100 different values, right? So that logarithmic representation gives you some form of some parsimony in your models. So that's one thing that gives this a little bit more general than it seems. All right? Okay, so this is our standing assumption. We're going to use binary state variables. So that's Bob. Okay, so it's the blessings of binary. So we're going to follow Bob. Whenever you see Bob show up, the message is that there is binary variables are being exploited. We're making use of binary variables. All right? So let's follow Bob. All right, so I'll talk about the paper. This is the title of the paper, and so this is nested decomposition of multi-stage stochastic energy programs with binary state variables. This is available in optimization online since May. This is my student, Jikai Zhu, who's who made great implementation, made all of these things work. This is my colleague at Georgia Tech, Andy Sun, who's great at power systems modeling and optimization in there. So these are my co-authors on this paper. Okay, so for maybe the tiny fraction of you who don't know what SDDP is, I will review it. I think everyone knows it here, but just for the sake of completeness, I will review it. Then I'll talk about SDD-IP, which is the integer extension. I'll talk about some sufficient conditions on the cut families that one uses, along with the binary nature of the variables to make this algorithm work. And then I'll talk about specific cut families that we use, and then present some computational results. Okay, so we're talking about multi-stage stochastic programming and SDDP. We're going to work with the dynamic programming formulation of the problem. So this is what this is. So in stage 1, we have the expected cost to go function going forward. So that's this calligraphic Q. This calligraphic Q is an expected value function, expectation of the value function of the children associated with the children. That's this regular QM. This is the xn is the node, and m is its children node. So this is the optimization problem in node m, which is a child of node n, right? So this is the optimization problem. Okay, so this is just just some notation to set us up. All right. In the linear programming setting, these value functions are value functions of linear programs. Of course, by recursively, we start. How you show it is that you start from the end. That's a piecewise polyhedral function. You recurse back, and you see again it's a piecewise polyhedral function. So essentially, these value functions are all convex polyhedral functions. One thing you should know that in the setting that I'm talking about, these variables are binary, but these are mixed integers. So they could have general integer variables. The local variables, the stage variables I don't have any restrictions on them. Okay. So how does SDDP work in the LP setting? So another fundamental requirement is this notion of stage-wise independence. So essentially, we have what is called a recombining scenario tree. In every stage, we have a set of realizations, and because they're independent and they're built from independent sampling, you can go from any state to from any other state in the previous stage. And so you have this kind of a scenario tree. So the main compression that it does is that essentially we need to maintain one value function per stage rather than a value function per node of the tree. Right? The nodes of the tree is path dependent, so this can explode. This gives a very, very kind of small parsimonious representation of the models. We just need to have one value function per stage. And that value function encodes the policy. This is the remarkable nice thing. We don't have to know the solution vector corresponding to this large tree. The actual solution vectors are all path dependent, right? But it implicitly encodes. If you give me the value function, I look at the observation, I solve the problem, that gives me the action for that stage. Right? So it's a very powerful encoding mechanism. So that's kind of this is the idea of dynamic programming. You can call it dynamic programming, or in this case, we are going to call it SDDP. So here's the classical paper. I think everyone's read it. So it's been 25 years, right? So in this session, there are 5 dedicated sessions with the title SDDP. I counted. I don't know, there could have been more, but I know at least there are 5. And I counted 22 talks. That's nearly 10% of the presentations with the title SDDP, which is remarkable, right? So, of course, we're in Brazil, so we're a little bit biased, but I think this is a remarkable algorithms, right? So, so let's see what happens. So just to here's a little bit of an animation for this SDDP algorithm. Again, just for the few of you who don't know what this is. So we have these value function approximations. So this is a 4-stage problem. There are 3 value functions, expected cost to go functions that I need to build. And so these are the real ones, which I don't know. So what does SDDP do? So it basically generates a sample path through this scenario tree. So that's the sample path. And along this sample path, because at every node, what do we need? We need the action from the previous stage, and we need the cost to go function from the future, right? An approximation of the cost to go function of the future. And in the forward pass, by having, it starts with trivial approximations of the cost to go functions, and solve the problems, and generates trial points or candidate solutions corresponding to each of these stages, and those are the candidate solutions. And then, so this is a one sample path, and these are the solutions corresponding to that. And then starting from the last stage, it solves all the problems. It solves all the problems corresponding to the last stage. And then, because now you have solved all the problems, you have an exact evaluation of the cost to go function, or the value function, at that point. And also using linear programming duality, we have a tight cut at that point. And that's the Bender's cut. That's added in the last stage. Now we go back one stage ahead. And now, at that stage, we solve all the problems, but with the value function approximation that I just updated. Now notice that this is a value function approximation which is not exact, it's not complete. So therefore, the cut that I generate is not necessarily tight, it's lower, right? So this is where you have to work for, when you try to prove convergence, you have to make sure that all of these things kind of line up eventually. That's the idea. And so if we go back one more stage, again, the cut is a little bit looser. There were some interesting talks on kind of how to deal with these things, issues here. And then we generate, again, another path, and then we keep going that way, right? So this is kind of how it's successively improving these value function approximations. It is a stochastic algorithm because in the forward pass, we are sampling, right? We are building this approximation at random points. The forward pass generates candidate solutions along sample paths. So the average of these gives us some kind of a policy, an upper bound estimate of a policy. It's a statistical estimate. And then but the cuts, they are valid. So they are valid, so they're always a lower bound. It's a deterministic lower bound on the optimal objective function value. And so that gives us, so in the first stage, once we have solved the problem, we have a value approximation. And so we have upper and lower bounds, and the lower bounds are going to be non-decreasing because we're never throwing away cuts. The upper bounds are stochastic, so we typically have this kind of a trace, right? So the lower bounds are non-decreasing and the cuts, the upper bounds are stochastic. And so, the algorithm has been analyzed in many different settings and under many different analyses. So the result is that if sampling is done with replacement and basic dual optimal solutions are used. In other words, we have to have, at every point, we have a finite set of cuts to choose from. Obviously, if this was a smooth function, if the cuts are not finite, we might run into difficulties. Then with probability 1, this algorithm converges in a finite number of iterations to an optimal policy for multi-stage LP, right? Now, so this is a little bit different statement. We say with probability 1 within a finite number of iterations, right? So when we say an algorithm, in a deterministic algorithm, we say this algorithm converges in a finite number of iterations. That means I can produce the number for you. I can give you an upper bound on the number. Here, such a number exists, right? But I cannot tell you from ahead of time. So there's a little bit of subtlety in this statement. Plenty of analysis that started, all the way from 1999, it's still going on. I see kind of renewed proofs under different conditions for this statement. On all of these things, the structure, the polyhedral nature, and the convexity is crucial in proving the convergence of this algorithm. Okay, integer variables destroys the convexity, obviously, right? So we have non-convex value functions, and we are relying on piecewise linear approximations. We'll still live with piecewise linear approximations. There could be other types of approximations, but that's what but what we have going, and this is kind of the primary motivation for having binary state variables, is the simple observation that any function of binary variables, doesn't matter what its shape is, can always be represented by a piecewise linear function which is exact at the binary points. Right? This is a trivial observation. So there again, Bob shows up. So that's what we're going to try to do. Okay, so there's another thing that we'll try to do. So here is the problem formulation. So remember, these are the state variables which are binary. What we're going to do is going to make a local copy of the binary variables. Right? So local copy of the state variables. this is the variable from the previous node, its parent node or previous stage that affects the decisions in node n. I made a local copy Zn. I added bounds on the Zn variables, so this is 0, 1. It may be integer as well, but just putting Zn to be a continuous variable is good enough, but it has to be bounded. And then we just write this simple reformulation which says Zn is equals to Xa of n. That's nothing remarkable. We just made a local copy of the state variables. Is that okay? Good. And then, of course, Xn is binary. Why did I do this? Again, it's a little bit of notation. I've just absorbed the bounds on Zn in this set. So let's just call it X prime. Just absorb the bounds. There's nothing special going on. But these two problems are clearly equivalent, obviously. But then what we can do is we can replace the constraint that I just had, X prime, by its convex hull. If I could get it, I just replace it by this convex hull. Then these two, and so this theorem says that these two problems are equivalent. Okay, so remember we replaced it by the convex hull, which means that if I added all the cuts corresponding to the subproblem, we relax all the integrality of all the local state variables. The only thing that I have is maintaining the integrality of the binary variables. So this is an equivalent formulation of the original problem. And this is true, and you'll see in a minute. I'll try to make this point very clear in a very simplistic cartoon. This is only because the variables are binary. All right? So that's, again, Bob is showing up there. These two problems are equivalent. So just to kind of illustrate why this is true, and those of my friends working in integer programming know this as this is like an elementary observation. But so here is a non-convex set. And kind of these are, let's say, this is an integer variable on this axis. And this is not a binary integer variable. Let's say it's a general integer variable. So what did I do? I said, OK, let's replace the non-convex set by its convex hull, right? And then I impose the binary nature of the variables that I'm interested in. So that's the convex hull. And now I said, let's get the variables to be binary. Right? So when sorry, not binary, integer. Right? So these are the integer variables, but notice that I've relaxed the problem because I have introduced additional stuff in this set. Right? So this is not an equivalent. It's a relaxation of the original problem. On the other hand, if my variables are binary, not general integer, right? So this is now 0 and 1, for example. I have a non-convex problem. First thing I did, I added the bounds on the problem, and then I convexified. So that's the convex hull, right? And so now I can, that convex hull intersected with the fact that that X variable is binary gives you the exact formulation. It's obviously a fairly simple observation, but it is the basis of all cutting plane-based methods for solving two-stage stochastic integer programs with binary first-stage variables. This is basically why everything works, right? Otherwise, we'd have to add cuts which link multiple nodes together, scenarios together, and you would not get the decomposition that you want. This is this fundamental observation. So therefore, you'll see that, I'm sorry for the typo, you'll see that we have plenty of papers on solving two-stage stochastic programs with 0, 1 first-stage variables. So here, what I just presented here is just kind of a generalization in the multi-stage setting. Okay, so this easy observation is going to be crucial as we go forward. All right, so now I introduce a local copy of the state variables. Right, so this is my local copy, and then I equate it to the state variable from the previous stage and the binary nature. So these are the node. So in the forward problems, I solve these node problems, right? So I have these stages, and these are the number of, J is an index of realization in each stage. Just for simplicity, I'm assuming the same number of realizations in every stage. And the probabilities are equal, so this is kind of the expected cost to go function. By the way, I should mention that all of that I talk about here, except the sampling part, would work if you had a general scenario tree. You just have to maintain a subproblem for every node as opposed to maintaining one for every stage. Okay, so what do? We are going to replace in node J, right? So we're going to, the node J subproblem is going to be relaxed. There's a Q bar. This was Q. Now I have Q bar in iteration I. The superscript is iteration I by an approximation of the cost to go function of the future. Right? This is the cost to go function. So I is the iteration counter, T is the time period. And these cost-to-go functions are going to be based on piecewise linear approximations, as before. This is exactly vanilla SDDP or nested benders, whichever you want to call it. Now, in this case, the cut, because I have integer programs, the cut coefficients in SDDP, we solve the LP, and we get the duals to get the cut coefficients. Here we're going to solve perhaps some kind of a relaxation of the original problem and use those to get the cut coefficients. So here is a sufficient set of conditions for things to work out, right? So, of course, the cuts have to be valid, which means they have to be lower approximates of the real value function at the binary points. I don't care if they are not valid when x is fractional, obviously, but they have to be binary. Here's another requirement, which is a little bit, let's pay a little bit attention to this. So this is the cut that I obtain in iteration I, has to be tight to the approximation that I get in iteration I plus 1, right? So at that point, because after I add the cut, it has to be tight. But notice that this is not Q, this is Q underbar, right? These are the approximations that I build in, because obviously I don't have the full value function, I am only approximating it. So once you have this validity and tightness, you can prove convergence. But then, of course, if the possible cuts that you can select at a particular point is finite, then you have finiteness also. So these three are sufficient conditions that allow us to have this result, along with the binary nature. So of course, we have to utilize the fact that what we are optimizing is over the binary hypercube, some subset of the binary hypercube. Using those, we can prove convergence, or a finite convergence of this algorithm. Again, Bob shows up here. Okay, so we need to kind of come up with reasonable cut families, which are computationally useful, that satisfy these conditions. I'm not going to go through the convergence proof. I just want to get some ideas, because there are some subtleties, but I'll just skip those. Well, let's talk about what type of cuts we can use. So at every node, I have a subproblem, which is a mixed integer linear program. Right? I could solve its linear programming relaxation, obviously. A linear programming relaxation is always going to give us a lower bound. I can use the duals corresponding to that. This is what has been used for solving SDDP, applying SDDP to multi-stochastic integer programs, because the lower bounds are valid. Right? So you would do Bender's cuts. That gives you a valid lower bound. And in the forward pass, you would solve MIPS. That will give you a feasible policy. If you're lucky and the bounds are close enough, you're done. Right? But you cannot, that's not going to be an exact algorithm. But certainly these are valid and finite if I use basic dual solutions, but not necessarily tight. There is the integer optimality cut that inspired by the two-stage Laporte and Laveau paper, which is only true for binary. Essentially, all this is saying is that, okay, at a binary point, I solve the integer program. Your cut is such that it is tight at that point, but all the other binary points, it's very loose, right? It takes another value, which is some lower bound L. I'm not going to go into the details of this notation, but essentially that's what it is. So it is valid, tight, and finite, right? So immediately we have the algorithm that we want, right? So it's essentially an extension of the Laporte and Laveau algorithm to the multi-stage setting. If you've ever tried to use this algorithm, it's not very, you have to do a lot of tuning to make it work, because the cuts are very, very weak. Right? It's almost enumerating all of the binary points. I wanted to mention kind of this paper by my student Gustavo Anhulo, who's here, and that's Gustavo, and my colleague at Georgia Tech, Shantanu Dey, where we have proposed some improvements to this Laporte and Laveau cuts, which essentially works with one point at a time. But if you have visited a whole number of points, you can strengthen the cuts by essentially looking at the convex hull of the points that you've explored, and combining with a kind of a trivial subset which you have not explored. So that gives you somewhat strengthening of those cuts, which can help sometimes. So if you wanted to use the Laporte and Laveau LL cuts, maybe an improved version of this is better for this context. Okay, so the cut that that I would like to talk about is these Lagrangian cut. So what is the Lagrangian cut? So this is the Lagrangian relaxation of the problem at a node j in time period t plus 1. Essentially, I have this constraint which says that z is equals to x. So I made a local copy of the state variable, and I equated with the state variable, and I just take the Lagrangian dual with respect to that constraint. And I solve the Lagrangian dual, and essentially that gives us this cut. Right? So it's a trivial algebra. So that gives us like this Lagrangian cut. Of course, it requires us to solve the Lagrangian dual. If you use kind of this, Lagrangian function is piecewise polyhedral. If you only use kind of the extreme basic dual solutions, it is valid, fine, and finite. And then you can show that this is tight, right? It is tight only because of the binary nature of the state variables. Right? So again, Bob shows up. And that this tightness result follows from a well-known result in integer programming, which characterizes the primal, the primal characterizations from the Lagrangian dual. It does a convexification. Because of the local copies of the state variables and the binary nature of the state variables, we essentially have these kind of this facial property. Once you fix to one and you fix to the other, you basically get the same set. And then this is applied recursively. Remember that it's not as straightforward as that because it has to be applied recursively because we fold it in as we go forward. So this is the kind of the part that needs an induction step to go through. Okay. Again, I'm not going to go through the proof of this, that this family of cuts is tight. It's always going to give you a kind of tight approximation of the value function. So I'll just illustrate it. The reason for this illustration is I wanted to kind of compare kind of the well-known Lagrangian cuts that is being used in the SDDP world. So here is a mixed integer problem, right? It's a trivial one. You're trying to minimize y1 plus y2. This is the state variable, x. And this is kind of these are the local variables. I have one integer variable and one continuous variable, right? So 0, 3. So this should be 1, actually. Sorry about that. Y1 is between, no. So I apologize. No, this is okay. So I have an integer variable which takes the values of 0, 1, and 2, and then I have a continuous variable. This is what the value function looks like when you project it onto the space of the state variables x's. So the Lagrangian cuts that I've seen being used essentially dualizes the linking constraint in the problem, right? So it dualizes the linking constraint. And so, for example, in these papers, and so once you dualize the linking constraint, and you get a Lagrangian cut, which is this one, right? It is not necessarily tight. It is oftentimes stronger than a linear programming relaxation. But in this case, actually, this is just equal to the Bender's cut, and there is good reason for doing that. What I'm talking about is actually making a copy of the state variable, z. And then, okay, if you have the z to be continuous, you get this cut, which is a cut of the which is tight, and is a cut for the convex hull of this value function. And more, at least in the simple example, if z is allowed to be binary, which you can do, it actually gives you the cut which is essentially a facet of the convex hull. Okay, so there's very good reason for making this local copy of the state variable. So if you take away one message from here, one of the is to please make local copies of your state variables. Okay, if you have integers. If you don't have integers, it doesn't matter, right? All right, we're not going to solve the Lagrangian, solving the Lagrangian dual type, but might take effort, so you can take heuristic cuts, basically just solve the LP relaxation, use the LP duals from that constraint as your approximate multipliers that gives you valid cuts. Not necessarily tight, but you can show that they dominate the Bender's cuts, and they are incomparable to the Lagrangian cut. So there could be regions where that cut is stronger. We have examples of that in the paper. All right, so in the 5 minutes that I have, 3 minutes that I have, I'll give you some computational results. So this is a paper by John Pearl Watson, Sarah Ryan on kind of generation expansion planning. Without getting into the problem formulation, so first we have a small case where we have 10 stages, and each stage has like 3 nodes, which is a small problem, but the extensive form has a huge number of variables. Cplex cannot solve it. I'll just go through this small case to kind of compare the different types of cut families that I've introduced. So these colored parts represent the number of forward passes that you do in SDDP. So going from all the way to 1 to 50 forward passes. And this is the time. These are the different methods. So you can see that if I use just this integer L-shaped cuts, which gives you a valid algorithm, it doesn't work, right? It's too long. Whereas, so B represents, Bender's cuts combined with integer L-shaped cuts. That's one option. This is just the Lagrangian cut. Bender's combined with Lagrangian. These are what I call strengthened Benders, where I use LP duals. And so this is kind of the time plots. These are the gaps that remain after, I believe, 5 hours for the small problems. This is how the lower bounds are improving, and you can see that kind of the strengthened Benders for Lagrangian kind of dominates how the lower bound improves. And this is the kind of the larger problem, right? So I have like 6 or 9 stages, and each stage you have like 50 to 30 realizations. And so the extensive form is, of course, unimaginable, like it's 11 trillion variables, which is meaningless. But you can solve these problems, in let's say within reasonable time. So these are stochastic energy programs, which are like being solved by these methods in under 3 hours. Okay. So let me just summarize. We have extended the SDDP method to mixed integer stochastic integer programs with binary state variables. Critically exploited the fact that these are binary state variables, and at least so far the computational results indicate that the strengthened Bender's cut combined with the LL cuts seem to work the best, right? This is very, very preliminary experience with this algorithm, right? I think there's not a lot of work to be done, a lot of tuning to be done for this to be kind of used in kind of lots of different settings. But I am hopeful, and I'm excited by this progress, and hopefully it'll interest some of you kind of, if you're interested in stochastic, multi-stochastic IP, to look into this type of methods. Okay, so I think with that, I'm going to finish, and thank you very much for your time.
Thank you, Shabbir, for the stimulating talk. Are there any questions?